So this is second lecture, a whole series about 10 lectures on literature and history of mathematical science, hosted by CMSA in Harvard, cooperating with Tsinghua University. So today we have Okounkov and Conrad Walker will be chairing this session. Conrad.
Thank you. So it's a pleasure to have Andrei Okounkov giving the next talk in this series. Andrei is well known, so really he doesn't need introduction. Not only he's well known in the math community, but also among physicists because of the important impact of his work in physics. But just for the sake of completeness, let me say Andrei Okounkov is the Samuel Eilenberg Professor of Mathematics at Columbia University. He was born and educated in Moscow, and he came to the US in '95 and held position in the University of Chicago, UC Berkeley, and Princeton University before joining the faculty at Columbia University. He has done important work on representation theory and its applications to algebraic geometry and mathematical physics. And he has been recognized by many awards and medals and so forth. Perhaps just to mention a couple among many, he's a recipient of the Fields Medal, as well as the European Mathematical Society Prize. So without taking more time, let's welcome Andrei, and his title is Classical and Quantum Integrable System in Enumerative Geometry.
Well, thank you so much. Thank you, Yao, for this invitation to speak, and thank you, Kumran, for this very kind introduction. And it's really an honor and a pleasure to be addressing you on this topic. And well, the subject is really old and really broad, and so I will try to give a very general kind of the reason I have this model of the hyperbolic plane here in the picture is because the subject is kind of like a hyperbolic plane. Means if you go a fixed distance from any given point, then the volume of the things to discuss grows exponentially. And so instead of trying to cover the whole subject, I will follow one particular thread, just kind of like in this picture, and that thread will lead us from the very early days of research in the relations between quantum integrable systems, classical integrable systems, and enumerative geometry. And some things are relevant today. So this is also also the video you're seeing. Those are solutions of the Korteweg-de-Vries equation, which I just took off YouTube. So I didn't do any research on that. I search. You can search YouTube for yourself and see what solutions of Korteweg-de-Vries equation look like. Now, so as I said, this will be a talk in a very broad subject, following one particular direction, and I won't be able to say much about many topics, but in particular, I won't be able to discuss the contribution of one person in the field who was among the pioneer of the field and very many important insights about the relations between enumerative geometry and integrable system. Very tragically passed away last year. So this is he was a great person and a great mathematician. And you can learn more about his work from many sources available. And so let's see, what do you think I would be? Oh, no. Trying to get the meeting controls out here. And so I imagine, so there are many things I should discuss, and then I imagine I can't really give an introduction to all possible topics. In particular, I will kind of imagine what Grom-Witten theory is, and if you don't, there's a very nice volume edited by Kumran, which contains a lot of information about its significance in physics and in mathematics. Very briefly, so you consider, so if you have some algebraic variety X, which will be called target, then you'd like to study algebraic curves in that variety, and then so there'll be some moduli of you think of curves as parameterized curves. There'll be some moduli space of a curve, some abstract curve C of some genus, and a map of some degree to your variety X, which I kind of depicted here in the picture. And then you'd like to say, well, maybe I want to count curves that come that meet 3 given cycles. Here I draw another curve, like a curve alpha and a curve beta, and maybe divisor gamma. And so this is the way to phrase that a curve meets a cycle is maybe you integrate over the moduli space, you pull back via there's evaluation map at the mark. You introduce marked points on the curve, you pull back. You have an evaluation map at those marked points that goes to the X, and you pull back some cohomology classes from X. So that, and then you integrate. Well, you integrate. Your integration is strictly speaking against a certain virtual fundamental cycle, because that moduli spaces are very complicated. Some very complicated base, but that's the gist of it, and that is what it is supposed to represent mathematically. Is supposed to represent topological string that propagates in X. So that's all you can read all about this in this volume. But then if you're interested in just these quantities, maybe mean the quantities that tell you in how many curves give of some degree in genus meet given cycles in X, these are not sufficient for the development of the theory, neither in physics nor in mathematics. And so you introduce, in addition to this kind of primary counts, you introduce descendant counts. And so what are these descendant counts? Descendant counts is when you to every marked point you want to know, you record something that happens in the neighborhood of that marked point, and this would mean what? You introduce there's a line bundle over your modular of curves, namely whose fiber there's a collection of line bundles over your modular of curves whose fiber is the tangent line at the ith marked point. And so maybe more geometrically, you would rather think about the cotangent line, which cotangent line at ith marked point means just a local coordinate at that ith marked point. And so this is some line bundle which will have a Chern class. So one denotes psi I, the first Chern class of that line bundle. And so then, in addition to your primary invariance, means in addition to integrating classes that are pulled back from X via the evaluation map, you also twist them by this the Chern powers of this Chern class. Like I said, this has to do with the behavior of the map in the neighborhood, this marked point, like the derivatives of the map neighborhood. So it's like a condition on the derivatives of the map. It's not just where the map goes, but also what the derivatives do. So these are this descendant insertions, and one in traditional notation for them is this tau notation, where you indicate its descendant tau in the argument of the tau. You indicate descendant of which class it is, and in the subscript you take which descendant. So, and so then once you have this, then you have in principle infinitely many things to compute, and you can form a generating function, which means you convenient way to form a generating function. You take an exponential of all these possible descendants, assertion and weighted with some variables tki. So you have finitely many cohomology classes on X and incountably many descendants, of which one of them, so we have like a finite by infinite array of variables, and you take formal sum of them, or just sum, and then take exponential, expand it in a formal power series, and integrate it. So that would be the Cron-Witten partition function with descendant. And so it's a function of a whole bunch of variables, and you would like to know what this function is like. And then and so this is the subject really starts with the kind of amazing conjecture by Witten, which goes back almost 30 years, is that if X is not some interesting algebraic right, just a point, then means you don't have to integrate over maps, you just integrate over modular of curves. Then this generating function, the which I just wrote down, it's something called the tau function. My understanding is that the tau function, I think the tau, the two taus, and the fact that some generating function for this taus is the tau function, I think it's unrelated things. I think it's just a happy coincidence. I'll explain what the tau function is. So it's the tau function for something called the KDV hierarchy, And so it's either the tau function or it's exponential of the tau function, depending whether you think about connected or disconnected curves. It's the usual thing. If you have a generating function over connected object, that's the logarithm of the generating function over disconnected objects. And so then it's easier for us to think about disconnected things. So it is just a tau function if you cook it like this. And right, so this is the KGV. The KGV. I will explain what the K. I mean, I will not really explain what the KGV equation is, but we'll get there. And so then and so what? Like I said, it was really an amazing conjecture, and what led to this conjecture is that this same tau function was found earlier in different. So you can, instead of integrating over modular curves in kind of an algebraic geometry, you can approximate these integrals by matrix integrals techniques, and there, so that would be like a matrix model of quantum, two-dimensional quantum gravity, and then it was found earlier in the analysis of those matrix models that they described by exactly this tau function of the KGV hierarchy. And well, we'll say more about random matrices when we a little later in the talk. And so now this is, we will now start with the discussion of classical integrable systems, and of course this is a huge field, and then it has a big literature. The book I like is this book right here, which contains a chapter by Arnold and Giventhal about symplectic geometry, another chapter by Novikov, Krychever, and Dubrovin, who I mentioned earlier, about integrable system. I think it's a beautiful read, and in English it costs a lot of money. In Russian it's free. Maybe it should be translated to Chinese for some reasonable price. Anyway, it's a great book, and here I have a picture of a very basic integrable system, which you can visualize, namely the geodesic flow on an ellipsoid. So geodesic flow is the flow on the tangent bundle to a manifold. So an ellipsoid would be a four-dimensional manifold, and that geodesic flow, it's completely integrable in the sense that, so what's a completely integrable system? Classical, from the point of view of symplectic geometry, well, it's just a symplectic manifold M, it's the phase space of your dynamical system, together with a Lagrangian projection, Lagrangian fibration with some base. And so the functions on the base, they would be commuting, Poisson commuting functions, and so the corresponding flow will commute as functions on the fibers. And on each fiber, that will be just, since each fiber is a torus, on that fiber, the flow would be just linear, kind of linear flow. So it means it will be quasi-periodic motion on each torus, and so that's you can really see, in the ellipsoid example, you can really see. In the Korteweg-de Vries equation is so Korteweg-de Vries equation is an equation for shallow water waves, and that's it's in principle an infinite dimensional classical integrable system. Some of its tora are finite dimensional, and then you really see this picture. Some of its tora are more infinite dimensional, so that means it's a combination of infinitely many harmonics. And by the way, some solutions of the KGV equation you saw at the beginning of the talk, and also they're plotted behind me against the New York City skyline. And then it gets, it's reflected in the New York recovers from 1925, and in the recent one, reflecting this kind of new development. So the reason I have this picture is that because there'll be another New York recovery at the end, so we'll get there. But maybe right now I'll switch to a more traditional picture of KGV solutions. So anyway, that's the classical integrable systems. And then, and what's the main example? Maybe the prototypical example are this Beauville-Mukai type integrable systems, where your phase space is a space of one-dimensional sheaves on some Poisson surface, and these sheaves are So this Poisson surface, the symplectic. So for concreteness, you can take the surface B projective plane, the symplectic form be dx over x, wedge dy over y. So this would be this gives projective plane a Poisson structure, well, the one of many. And so that that Poisson structure degenerates along the toric divisor and projective plane along the 3 lines. And so my sheaf, if I fix what the sheaf does at those lines, so I fix the points of intersection. I fix the point of intersection at the, so here's my sheaf is one-dimensional, it's a curve. If I fix the point of intersection with that divisor, then I get a symplectic manifold of dimension 2G, which G is the genus of the general curve in that family. That's bijunction. And so then with this projects the Lagrangian fibration here is that you have a one-dimensional sheaf. So maybe the way to think about it is you should think of the base. The base are curves meeting my particular anticanonical divisor in a given collection of points. And so that would be a G-dimensional family of curves of genus G. And then the fiber are line bundles on this curve. So you just sheets on the plane, so line bundle on each curve. The projection forgets the line bundle. So this is the fibers are G-dimensional tori, the Picard. So that's the the Picard varieties of curves, and the base is a G-dimensional projective space, some linear system. And the way it's usually appears in the integrable system is that the curve, usually there's some auxiliary linear problem, and so it's some linear operator depends on variables. So maybe the linear operator depends, some matrix depends on variables x and y, and then the curve would be the determinant. So that would be the curve would be, people say, spectral curve. So it's where the determinant of that auxiliary linear problem vanishes. So it's some matrix, some size depending on x and y. You set determinant of that be 0. It's a curve in x and y. And then on that curve, I have a sheaf, namely the eigenvector itself. So normally a line bundle. And so that would be, so this is an example of this. And so so that we don't maybe we don't jump to conclusion too early. I had before some curve of genus G and it was denoted C, and now I have another curve of genus G also denoted C. Maybe that was slightly, so maybe this is slightly misleading because it's not like these curves here have something to do with the curves in the previous problem. In fact, so the fact that here's a family of curves, there are some modular of curves, that is not, to the best of my knowledge, nobody can connect quite like that, because the solutions that come from Witten's conjecture and other solutions that come from numerical geometry, they're not really of that flavor. You have to do something else to make them of that flavor. And the curve C anyway, it's not something. The curve C is not something that that related to the curve itself. It's more something related to some mirror variety and things like that. So it's not directly related to the questions we discuss here. Just, I mean, the two things are not. It's not the same curve. Maybe let's say it like that. and so what's a tau function? So a tau function is a section of a line bundle on the moduli. So this is what kind of line bundles on the moduli of shifts we have. Well, it's usually some determinant of cohomology. So for since we have a family of abelian varieties, that is some tau function. So tau function. So what's a tau function? Tau function is a function on an abelian variety which vanishes when your line bundle picks up an extra section. And so that's so this means some determinant of cohomology of your sheaf vanishes. So that's the section of that line bundle is a tau function. So so this is if you look at the KGV solutions, the formula for KGV solution for quasi-periodic solution, the KGV, the formula, the Matveev-Fitts formula for that is this actual solution is like the second derivative in x of the logarithm of some theta function. That's the theta function. That's what we're discussing here. And so for us, it'll be, rather than dealing, like I said, we will not be dealing with finite dimensional abelian varieties will be this the solutions we need are really kind of infinite. I mean, they really have to do with infinite dimensional geometry. And so the way to do it is conveniently like this. Suppose you have a mark, but like in our case, we have some point. One of the points at infinity. You think of a point at the divisor of the anti-canonical divisor is a point at infinity. And so then suppose you choose a coordinate, and then if I have some sheaf, I can take its section twisted by something very, very ample. So that would be, I can take those sections and look at their expansions in that in the formal series and that near that point P. And so this would be some subspace of a certain dimension. And that subspace would be commensurate with just regular functions, right? So this is if you want to talk about the determinant of cohomology, the thing to discuss is that since determinant of cohomology is related to like the determinant, some sort of determinant, some large determinant related to the space. So the way to discuss is this Plucker embedding of half infinite Grassmannian. So we take an infinite dimensional space, in this case, formal Laurent series at the mark point P. So they're finite dimensional you have a finite expansion in negative powers of x and formal powers x and positive powers of x. So that's some space. And then we look at the Plucker. We look at half infinite. We look at half infinite dimensional subspaces, space that commensurate with just regular functions. And so the home for this is you take the semi-infinite Grassmannian. That would be this thing called the fermionic Fock space. So this is an example of that. Maybe I should write. It's an example of that. Is some half infinite wedge, like you take x to the -5, x to the 2, x to the 3, x to the 4, and so on. This means the span of all these monomials x -5, x squared, and so forth. So that's a point in this half infinite wedge space. And so this is the determinant or the tau function becomes just a coordinate in this. So it's a particular coordinate in the space. This Plucker embedding of this half infinite Grassmannian. And so this is the discovery of very classical discovery people now called Kyoto School. It of course involves many individual people, and some of whom I mentioned here. And there's a great book to read about. They wrote this book by Jimbo, Miva, and Date. Says talk about solitons. So this I hope you'll. It's a very thin book. You can all read it from the beginning to the end. Would be a great. I'm sure it'll be great reading. And so in this, rather than discuss the KdV equation. Now I haven't written what the KdV equation is, and I will not reiterate what the KdV equation is, because I want to discuss a more general equation. So more general than so KdV is a particular case of Kazantsev-Petriashvili equation, and then the Kazantsev-Petriashvili equation is a special case of something called the two-tone equation, and so I'll discuss that two-tone equation now. And so this is what is this two-tone equation? And I remind you that there is. I remind you that there's so this is a very, very simple case of general discussion discussed in Victor Katz's book, and so also in the Soliton book they'll be discussed very clearly, but also so this is another place to read about it. So we had this formal Laurent series in X, and this is like I said, this is an infinite dimensional space. We took its half infinite wedge power, means we take wedges of monomials that are commensurate with formal power series in X, and then on formal power series in X, we have an action of differential operators. So we can differentiate, we can multiply by X and X inverse, and we can act by differential operators. You can differentiate all that. So this action this action of differential operators. Differential operators act here, the space itself, but then of course if you think of differential operators as a Lie algebra, the Lie algebra, if a Lie algebra acts on a space, it also acts on its exterior powers. And so this Lie algebra differential operator, not the associative algebra differential operator, acts on this Fock space. And so that would be so this Lie algebra, the Lie algebra differential operator, that's more or less GL infinity, so which is up to some definition. But then of course, but then there's also the issue of a central extension. Means if you define it's usual in physics, if you define something, or in mathematical physics, if you want to define something, infinite, then sometimes you need to regularize infinite sums, and once you regularize infinite sums, your commutation relations are not exactly preserved, but preserved up to a constant. The constant depends on regularization. So that's the same story here. So this is, if you'd like to say, actually define the action of differential operators on this half infinite wedge space, there'll be some additive constant you have to pick up. So that's exactly the central extension of GL infinity. And so this is maybe to make this clear. So if I among the differential operators, I have multiplication by function, so order 0 differential operator. And so in particular, so multiplication by function, so does it mean that if I have multiplied by x to the k, then x cubed will go to x to cube plus k. And now if I, since it's supposed to act as a Lie algebra, so well, how does Lie algebra act? So Lie algebra, it's like, it's like differentiate. It's like act by Leibniz rule. So it means if I have a monomial like that, so maybe I'll underline with a different color. So if I have a monomial like that, so what does Lie algebra do? The Lie algebra goes and acts on every single term in that monomial. So for example, if I want to act by this alpha minus 2 is supposed to multiply by x minus 2. So this would be, first we get to multiply the first term, so we get x minus 7. Then we get to the second term, so we get x to the 0, and so on and so forth. So that's how it acts. That hopefully it's clear how Lie algebra acts. And then there's other operators related to x to the k. Namely, you can take just the wedge product by x to the k. Namely, if I act by the corresponding wedge product, it will just take wedge monomial to another wedge monomial. So this is not in the Lie algebra, it's not here, but the expression in the Lie algebra, they're bilinear. So for every number k, we have an operator alpha k and psi k, and alpha k is bilinear in psi, so this has this formula. So what does it mean? So psi, if I go over all monomials in my wedge product, if I can, psi I removes the corresponding guy. So if I remove it, and then I put another one k shifted by k steps. So this tells you people call this alphas to be bosonic operators, and psi be fermionic operators, and so alphas get to be they're bilinear. The boson is some quadratic expression in fermions. All right. So what was it? While I was talking, is that because our Lie algebra, so GL infinity, or differential operators in x, that Lie algebra commutes. So if I take it in Fock tensor Fock, this will commute with the operator. If I remove one monomial in one space and act, so if in one factor I remove a monomial and the other I put the exact same thing in, so I take the adjoint of the wedge product by xk in one factor, and in another factor I just multiply by exact same thing, that my Lie algebra commutes with that. And so this another way of saying is that if I have some vector space V and some other space V dual, then in that space there's a canonical element, kind of canonical maybe it's like kind of identity in V. So this is canonical element, means a GLV invariant element. Right, so this is, if you think of the space as endomorphism for V, that's the identity as automorphism, and they can act by this in the wedge algebra of V, tensor wedge algebra on V. In one instance you take the wedge product, in another instance you take the contraction with this. So in the first factor you take, so this here Vx by, in the first factor Vx by tensor product, and the second factor V star, the dual space X by contraction. And then so this is the way to write Pluck relations. So Pluck relations say, so if you want to know, so the matrix elements, so what are the matrix elements in the tensor product of two, one wedge algebra tensor, another wedge algebra? The matrix elements are bilinear expression in the minors of your matrix. And then commutation with this element says that there's some bilinear relations between minors of a given matrix, and these are the Pluck relations. And now we can finally, after the discussion, I can finally say what the tau function of the two toda. The tau function of the two toda is, I take, first of all, it's a particular matrix element in the Fock space, so, or particular minor. So this is matrix elements in Fock space are minors of your matrix. So this is a particular matrix minor, and that minor corresponds to what people call the vacuum, or it's also the space. It's also the space we mentioned many times before. That's the space of that corresponds to regular functions inside all formal Laurent series. Okay, so that's a matrix element. And then what do you take under matrix element? You take a generating function. So alphas, they commute among themselves. So then, so the positive ones and the negative ones, maybe I put here the summation is over positive, and here's also over positive. So these two commute among themselves, and so then you take the generating function of these operators, much like we took in Gromit theory, and you sandwich with arbitrary matrix in GL infinity. That is the sandwich with your initial condition. And so why this thing satisfies partial differential equations? Because what will happen is that if I take, sometimes lose the scroller here, so okay here. So what will happen to this element if I take partials? If I take partials with respect to my variables Ti, what will happen is that these alphas will come down from the exponential. They will act on the vacuum, and so I'll get, if I take the partials, then I get a whole bunch of minors of some matrix, and a whole bunch of minors of some matrix satisfies Pluck relation. And so they'll say the partials of this function here satisfy some differential equations. So those equations are the two toda equations. So instead of writing the equation, I wrote you the general solution. So you can, sometimes you would, I think you would. So in math, there's something about writing equation, also something about writing solution. So both are important. I mean, sometimes you can argue, since you were hoping to use the equation to compute some numbers, and maybe it's easier to write. If I give you the solution, then maybe it's easier to deal with that. And in fact, it is. So maybe moral from this discussion is that the kind of main observation of the Kyoto school is that if I take a free fermion, which is some important quantum system, so this is the fact that it's free doesn't mean there's nothing to learn from it. It's a very good, very important quantum system. And if I take the vacuum expectation in that, or some other kind of partition functions in the free fermion, in this case I took the vacuum expectation, some free fermion operators, then I get a solution. So if I started with the kind of simple quantum integrable system, and I end up with a tau function. Tau function, like I said, I explain what this is. It's of a classical integrable system, maybe very, very complicated one. So this is The Kazantsev-Patviashvili, they describe Kazantsev-Patviashvili equation. They describe waves not in one dimension but in two dimensions. They kind of weakly modulate in one direction, and then Tuto, the equation describing. These are very, if you think of what this phenomena actually describes, are very complicated equations by this very simple. Now going back to the Witten conjecture, the Witten conjecture that this generating function now this is now in Gromov-Witten. So maybe I'll indicate the angle brackets generally in physics indicate, or in mathematical physics indicate partition function, and the partition function means you integrate over all you mean integrate over all possibilities, and fermionic situation integral means determinant, and the situation we discussed, we integrate over the moduli. So the Witten's conjecture was that if I take this generating function, which is this generating function for descendants for a point, that there's a tau function of the KdV hierarchy, and that's of course a very classical subject in mathematics, and this is really well understood in a variety of ways. If you want to read about Kontsevich's original approach to that, maybe the best resource is this book by Arbarella, Carnalba, Griffiths, and there's a contribution of Harris, which is the second volume of the Arbarella, Carnalba, Griffiths, Harris. It's really good reading, I must say. So I really encourage you to read. And then a fantastic proof was given by Mariam Mirzahani in 2003. Of course, also extremely. It's an unspeakable tragedy that Mariam is no longer with us. Here she is with Anahita. And those of you at Harvard, you can probably be. I'm sure you'll be inspired to think that Mariam was walking those hallways, walking the Harvard courtyards as she was thinking about her proof. So, and many other things. So that's right. Yeah. So that's it's an unspeakable tragedy. Another resource I really recommend looking at is this paper by Landau and Kazaryan, and its clear advantage is by far the shortest of all these proofs is that it only contains 12 pages, including references. And what it does is reduces the question about the point to the more general question about when they have a target, x equals p1, and what does it mean to have a target? It means you have a curve with a rational function. So so you not just have an abstract curve, but it has a map to p1. So it means you have a rational function on your curve, and that makes sense. That if I have a curve with a rational function, you somehow know much more about the curve, and that's and so this is so this is the Landau-Kazaryan proof is like I said, well, you read it. It's a very simple reduction to a more general case, and I think, and so so what is it? So maybe this is a picture. So I have a curve mapping to P1, and P1, okay, it's a Riemann sphere. And in fact, we can take P1 equivalently with respect to the action of automorphism, and automorphism of P1 will generally only have two fixed points, which would denote 0 and infinity. And then so this is some number Q that multiplies the rest by some non-zero complex number. And for P1, the analog of a Witten conjecture, that is a Toda conjecture, which starts with the Iguchi and his collaborators, and the final touches, and that were put by Ezra Getzler, who really pinpointed the actual relation between kind of Grom-Witten times and the Toda times. So this is well, anyway, some change. It's important to have a correct statement. That's important, and that so it says that if I have so maybe I should say where is the change of times with a linear change of times, and this is due to Ezra. But it's the same kind of thing we considered before. Now we have in the covariant cohomology we have two classes. We can take the class of 0 and the class of infinity, and we take their descendants. So there will be a sequence. This would be a function of two sequences of of times. Maybe we call them tk and tk prime. And also in this, I didn't say it explicitly before, but now we will maybe explicitly remember the genus of the curve. Means we integrate the Gromit-Witten theory. We remember the Euler characteristic of the source curve, but also importantly, we remember the degree of the map. So we'll have two variables. One remembers the genus. So the U will count, or maybe the minus Euler characteristics. Okay, so this will be 2g minus 2, and then this is the degree of the curve, and so then so this is so this the conjecture of the total conjecture says that this function now, instead of as a function of two sets of variables, that's now a tau function of the two-total hierarchy, which is the thing that we just discussed. And this is all is needed. All that is needed in Landau-Scuderian argument is a very easy special case of the statement, which I've proven in 2000. But this full statement is in the paper with Rahul, which is I think that sequence of papers about the Gromit-Witten theory of curve. I think it's still okay reading. I mean, the subject of course moved a lot. I mean, much further. So unless you want to learn. I mean, our first paper I cited it's an excellent place to learn about what's a virtual fundamental cycle. But maybe in terms of actual math, or maybe it shouldn't be your first thing. First thing I would recommend reading. But this sequence of papers, it's actually, maybe there's something to, even though much more powerful techniques are now available, that's still, maybe you appreciate the more powerful techniques if you first work for this. And so what we actually prove, we really prove directly. We really construct this whole thing as some construct this whole Kyoto school setup. We just see it directly in the geometric problem. So that's I think it was rather satisfying for us, and that I think that makes sense, because if you want to talk about maps from a curve to P1, then it totally makes sense to talk about in terms of Hawk space, because what's after all, if I have a map from a non-singular curve to P1, that map is a branched cover. So this will have a structure like the structure I described in the picture. So it means if I say look at some preimage of the point infinity, that at near that point, in some local coordinate, this map from this preimage to going here, this covering map could be, for example, you take the variable and you square it. Means if I go means the disk around this point wraps the disk downstairs twice. Or if I go around the loop near infinity, then I go twice around the loop about the preimage of the point. So this is and the total. So this is if I have a point in the target P1, I can ask what's the ramification profile of the map over that point. And in this picture here, I tried to describe. So maybe this is this both points. This point also has the local coordinate here really also goes to z prime squared. And so this would be, since they look the same, they must have the same formula. Means the ramification profile over that point in infinity is 2 and 2, and this 2 and 2 is together a partition of degrees. So the map has some degrees here, degree 4, and so this is a ramification profile over any point. It's some partition of that number degree. Also, if I go around any other loop in my P1, then of course what will happen? So this will happen that the preimage of this loop is the bunch of loops in the curve that will cover my loop, some number of times. Here, this loop is still covered 2 times here and 2 times there. So it's again, the profile is 2 and 2, but in my picture here, if I go around this loop, then it's covered, then there's the preimage has 2 loops, and one covers with degree 1, another covers with degree 3. So the profile is like 3 and 1. And anyway, so this is all this data is the data of partitions of some given degree. And so this describes the ramification profile. This describes the monodromy of your cover, which is some permutation. And there are also partitions describe a base in the Fock space. Right, and this is you will if you don't know about this already, you will enjoy reading about this in this Soliton's book. It's very natural, and or you can think for yourself. And so, and in particular, if we want the remember the degree of the partition, so the size of the partition is the degree of the map. Well, this is our old operator x d by dx, which is also, if you think about Virasoro, this is the L naught in the Virasoro. So this is my operator, which was q to the degree. That is the same as q to this L naught. So that's one of the many operators you can write, very natural. I mean, all many others. And so so this is what we do is really construct operators. They're not exactly the bosonic operators, but they conjugate to bosonic operators. Namely, if we construct some commuting operators that they conjugate in an explicit way. I mean, they're from the point of view of integrable system, they're just as good as bosonic operators because just there's some angle, there's some conjugation, but it's not particularly important in explicit conjugation. And so then this is conjugate to this operator alpha k, and then there's some linear combination, some correction, some linear combination. It's like this is like in this combination here. It's like in Gessler's change of time. Change of time. So this is this corresponds. This is an operator that corresponds to insertion. This is an operator that corresponds to insertion descendants at 0, and the descendants at infinity are just conjugate operators. And so that we prove a formula that the partition function of P1 in Grove-Witten theory. So put this Grove-Witten here. That's just you insert. So in P1 you have this descendants of 0, descendants of infinity. That means you really put these operators at the so this here's your P1, and you really put an operator one end and operators on the other end. And in the middle, you just put the most natural thing that corresponds to the gluing of 2 parts. And so this says that this expression really does compute the Grove-Witten partition function of P1. It's in particular satisfy the 2 toes just by virtue of being a special case of the general formula for solution of the 2-toed equation. And maybe I should stress that this is what's in this formula is really a formula not for the whole P1, but in fact for a disk. So if I have what's written here is that the 2 halves of this formula are 2 halves of partition function for really disk. Out of the 2 disks you can glue P1, and so this is really what's happening, and this is some more general. It's really more general formula. And then maybe the moral from this part of the lecture is that quantum integrable system, they naturally live, from my point of view, they naturally live in the target space description. It's in the target space description, you get kind of a textbook while if you're working with the source or the moduli space of maps, then okay, maybe this looks like some kind of miracle, but in the target space, you really see the quantum and the classical integrable system really constructed in front of your eyes. And so now, since I want to say a few things about matrix integrals, is that if I want to know this vacuum matrix elements, what do I need to know? I need to compute things like matrix elements. So if I have some operator of this form, maybe this adds boxes, this removes boxes to my partition, and then in the middle, I'd like to insert some operator in the middle. And then if I ask myself, what's the distribution of the middle partition in this formula? So this means I sum over, like I was trying to start. I really have a formula for a disk, so I can ask, what is the mathematician say induced measure for the partition in the middle of this formula? And there's explicit formula for that. It's just some kind of hook length product there. And more importantly, that if I have that hook length product square, then it's some very general principle, which I will only mention very briefly, is that this partition behaves just like a random matrix. So it's not, there's a complete parallel. So partition is it's a really good discretization of a summation over partition. A random partition is really excellent discretization of a random matrix. And so this sums this matrix elements what we're discussing here. They really are both, on the one hand, they're both discrete, exact kind of finite size analog of a matrix integral, and also they're like I said, they're very directly related to actual geometry in the surrogate space description. It's really what it is. So this is now to continue the story. Of course, the two-tode is about this general integrable equation, as you will see in nature. Free Fermi, like I wrote here, just really entry level into quantum integrable systems. So you can ask, well, what about more general quantum integrable systems? And again, if you want to read about it, my favorite source is the book by Bill Ivan. I don't think it's translated in English. Maybe it should be translated in Chinese. So it's excellent. It's a wonderful book. It's like a kind of introductory course of theoretical physics. It has a introductory discussion of quantum field theories, but in particular of solvable quantum field theories, which is just, I think, a marvelous discussion. But also there are other sources to learn. And if you look, I don't know if your internet is good enough. If you look at the cover of Bill Ivan's book, then very faintly there you'll see the Young-Baxter equation. And of course, in the Cherry Presley book, you very explicitly see the Young-Baxter equation in slightly different way. And so we'll get to the Young-Baxter equation. So what I recall, so I spent some time talking about it. We had an action of a Lie algebra, central extension of GL infinity on this fermionic Fock space. That action is not irreducible. What is conserved is some like a fermion charge. So if you think of this as this monomials as Dirac C, maybe I should have mentioned Dirac earlier, but okay, now I do. Is that if you think of this fermions as Dirac C, then there's a total number. So then the number of electrons minus the number of positrons is the charge in the system. So electron is like a negative monomial that appears, and the positron is a positive monomial that is missing. So that's this charge is conserved. And moreover, if you think of this, how does Lie algebra act in that space? That's actually, well, the charge is integral, but in fact, the Lie algebra action can be defined depends polynomial in charge. So you can define a representation. You can define a representation, somehow for charge, which being an arbitrary complex number if you want, or an arbitrary element of your ground field. And as I said, there's the kind of the Pluk relation, the essence of the quantum rule system was that the action of this GL infinity commutes with this operator. So that's the Pluk relation. That's the kind of the essence of all this equation, is that it commutes with the operator, which is summation over k psi k tensor psi k star. That operator visibly increases charge, so it adds one electron. It adds one unit of charge to the first factor and subtracts one unit of charge from the second factor. So it's an operator like that. And I recall that the action, so again, the action of the Lie algebra in a tensor product is the action by the Leibniz rule, means in the two factors of the tensor product, some psi of Lie algebra X of psi tensor 1 plus 1 tensor psi. And now in the sequence, you had already had a talk by Pasha Ettinghoff about quantum groups. And then, and also Pasha not just gives talks, he writes wonderful books about quantum groups. There are many other quantum groups, including the one by Cherry Presley, which I already mentioned. And so what is the main, what's the main lesson from that that's important to us is that this whole picture has a quantum group deformation, namely if I take the universal developing of a Lie algebra, that's a Hopf algebra, and the coproduct is given by this formula here. This is a coproduct, defines a coproduct in universal developing of Lie algebra. And so now I would like to deform it to within the world of quantum group, means that deformed gets to deform to be a more general Hopf algebra. And maybe a good, people denote it by different things, but maybe a good notation for that is quantize double loops into GL1. And the reason why is that a good notation is because the single loops of GL1, this is where the alpha case, so alpha case RG is another notation for this is GL1 head. And those elements get to stay primitive, means they get co-multiply more or less like they're more or less like they co-multiplied before, and everybody else gets to be deformed. And so this is why this is a good notation. And then what we would like is we would like to deform the co-multiplication. So we deform the algebra. More importantly, well, as an abstract algebra, it's not going to be deformed; it's going to be isomorphic. But we're going to deform the coproduct, and we're going to deform it. So what would mean that instead of a coproduct, this will be now a non-commutative coproduct, non-co-commutative coproduct, and this will be deformed together with well, I'll call this space by space. So this operator S is called a screening operator, and so this is why I denoted S. And so this will move along, and this will be more general intertwiner operator. And this will have to do with the poles and zeros of the R matrix. And so I'll explain what this is. So when I get if I get this. So now we have some quantum group, which I denote UH bar, and then that quantum group has a coproduct. Means there's a homomorphism that goes to its tensor square. That coproduct is not co-commutative. Means if it depends if you put it in one order, you put it the opposite order. Means if I take the opposite coproduct where you take these two factors and permute them, you can see my cursor thing here. Then you get in principle a different coproduct. But the beauty of the situation is that there is an intertwiner, the R matrix, which tells you how to put one coproduct in the opposite order. That's really the most important. So this we would like to preserve that structure. So I mean, something called braiding or other things. But it's not. It's really so. This here the R matrices. And so this in particular we had a Fock module. So if I have a Fock module that has some charge C, and some Fock module has some charge C prime, and like I said, C and C prime could be variable. They don't have to be integers. And then if I take the opposite coproduct, means I co-multiply using the opposite, I act using the opposite order, opposite coproduct. Then then I should have a intertwining operator, the R matrix, which is now the indices of this R matrix are all the spaces in which it acts. But very, very importantly, depending on the C, this will be only depend on the difference of the C with respect to or the difference. What does it mean that we have a difference? So difference means the dependence on the C lies in some one-dimensional commutative group over. So this means we have some kind of group law on this set of C's, and that group law could be the additive group law, well, Mediative, you add numbers. Could be multiplicative group law, means you multiply numbers. Could be elliptic curve. So that's another option, which we're not going to discuss a lot. But in principle, so there's this three options, and depends three flavors of quantum groups depending on whether your this R matrix, what intertwines the two modules put in the opposite order, whether this depends on the charges as depends on their difference in the edge. And the difference depends on the ratio, means the difference in the multiplicative law, or depends on the difference in the elliptic curve. And of course, what the most important thing we want from this matrix is to solve the Young-Baxter equation. And so this Young-Baxter equation says that if I have now three factors and I can reorder them in two different ways, then these two should be equal. So this is Baxter's book is still wonderful reading. I think that you will still find lots of amazing stuff in that book. And in particular, what Baxter noted that and so Young-Baxter equation is called for two of the greatest physicists. 20th century had a lot of great physicists, but the two of them were Young and Baxter, and of course you can also, and so what there's some length of time between their work, and so what Baxter noted is that if the Young-Baxter equation implies existence of a large family of commuting operators, like for instance that if I take, so R matrix is like I said, it's some map from pair of spaces to pair of spaces. Now if I trace over one of the spaces, means geometrically, if I take one of these arrows and I just close it, means I take the trace. And in fact, I can even take a trace with some operator as long as this operator commutes with the R matrix. Then what remains, so this, if you think of that space as auxiliary, so I take the trace over the auxiliary space, what remains as an operator in the physical space, this will commute for any values of the charge in the auxiliary space. And this is how you get quantum integrable systems from solutions of Young-Baxter equation. But you also, in addition to quantum integrables, in addition to commuting operators, you get kind of stronger constraints, like you get flat connections and flat difference connections, like we also get in Gromit-Witten theory, and so on. And maybe I should point out here that it's interesting just in terms of change of variables, how the variables are matched on the different sides. Is that in this in the Baxter's world, so the Baxter's world, the typical meaning of that operator Z that's supposed to commute with the R matrix, well, commute in the sense that it stands to square commutes with the R matrix. There's the operator that for a spin chain defines quasi-periodicity and quasi-periodic boundary conditions. So it means it's an operator. So there's something like a quasi-periodicity. People give it only so much appreciation to that operator. But in our case, this operator would be directly have to do. This is really most important thing is this. It really contains the dependence on the genus. So so if you'd like to match what I'm saying with the quantum groups with actually enumerative information, you'd think, well, what would be the genus dependence? And the genus dependence is in quasi-periodicity. And so that's it's an operator. Operator here, this is more L naught. So exponential of anything times L naught commutes with the R matrix because, well, that's how things are. And then L naught is preserves our matrix, in other words. And then, but then the coefficient in that is the genus. So in the case of hand, so if I take, so this the quantum groups, very, very general things, but the ones which I'd like to would like to discuss here, they have to do with the double loops into GL1. And so in the additive version case, in the group for additive numbers, the the double loops into some Lie algebra would be like the Yangian of single loops. Yangian is for Yang, so for Yang of Yang-Baxter. So Yangian of single loops into GL1. What this Lie algebra is like? What's this quantum group is like? And then this contains many ingredients which are very important in other parts of theoretical physics. For example, the R matrix. This is known as reflection operator in Liouville theory, and this duplicate correlation. Yeah, so just very short screening operators, which are very important in conformal field theory in general. And so then for multiplicative and elliptic analogs, we get there's a Q difference in elliptic analogs of this object. So what's the relevance? So you can ask. So we want some discussions. We can ask, what's the relevance for a enumerative problem? And the relevance is that the Yangian version, it's really described. So instead of P1, we would talk instead of Gromov-Witten theory of P1, we can take a Gromov-Witten theory of a local P1. Means you study Gromov-Witten theory of a rank 2 bundle over P1, and that rank 2 bundle, the total space of that need not be Calabi-Yau. Of course, Calabi-Yau manifolds has millions of very important distinguished properties, but for this you don't need them to be Calabi-Yau. It can be anything. Like P1 itself was not Calabi-Yau, and you can take a bundle which is not Calabi-Yau. Total space of that is not Calabi-Yau. And so then you have the Gromov-Witten theory of that curve, which is also equal. This is some other set of some other direction which one can go and talk a lot about it, but I'm not going to do it. So this Gromov-Witten counts in that geometry are equal to Donaldson-Thomas count in that geometry, and so this this counts of local curves in threefolds or Gromov-Witten or Donaldson-Thomas counts. This was done more than 15 years ago now, and so there are the three flavors in which you can do. So in addition to Donaldson-Thomas and Gromov-Witten, there's also this quantum cohomology of the Hilbert scheme of points. So there's three things which are all interconnected. There's also orbifold. So this is like the fourth flavor. And so this was done. This object was done. Like I said, that was done before we understood the importance of quantum groups, but around 2007, Nekrasov-Shatashvili had this another kind of really amazing insight, which is I would compare it to the original insight of Witten, is that all of that should be really understood in terms of quantum groups, like I was trying to explain. So that's all of that computation should be phrased in terms of quantum groups, and indeed we with some work, so with Davesh Molik, we did it we defined the required quantum groups, or we constructed geometrically required quantum groups, and we redone the computation. So in particular, if you want to go this Gromov-Witten theory of local curves, there's now much easier ways that utilize this quantum group symmetry, and also or maybe Donaldson-Thomas theory of local curves are much easier ways to do it, and then also generalize, because instead of doing Gromov-Witten theory, instead of doing like quantum cohomology of the Hilbert scheme of points, one can do the quantum cohomology of instantons of arbitrary. So quantum Hilbert scheme of points are those kind of rank 1 instantons, there can be a billion instantons, U1 instantons in Nekrasov language, and instead you can do quantum cohomology of instantons of arbitrary rank, or you can do quantum cohomology of arbitrary Nakajima variety. All in the language of a suitable quantum group, and you can read about it in our introduction to that can be found too in these two books, which I since I wrote them, I can't really say they're good reading. Maybe senior you can find something. And then so this was about the Yangian. So somehow if you want a local curve in a threefold, that's about the Yangian of GL1 hat. So So this is, and now if you can, but the quantum groups you have in the quantum groups world, you also have the multiplicity. For people say trigonometric, that's another way of saying so. Multiplicity for elliptic versions, and the relevance of those is that if we want to do if you want to do the multiplicity for trigonometric version of this Yangian, but it's really you do quantum double loops into GL1 hat, that thing computes the K-theoretic Donaldson-Thomas count for local curve. And now this cannot be, and the formulas there are just so complicated, then it cannot be done with the quantum groups. I don't think so. We did it with Andrei Smirnov, but I'm absolutely certain we wouldn't be able to do it without quantum groups. And then more generally, so I keep emphasizing the target space description, and so more generally, so if you think about the target space description of geometry of a local curve, that's some quantum field theory in 2 + 1 dimension, meaning you have two dimensions of your curve, and then also time. So it's a compute in K theory, means you compute some indices, there's some time. And so this language is very instrumental in discussing more general 2 + 1 dimensional quantum field theory with 4 times the normal amount of supersymmetry. And then you can do computation in those theories using these quantum groups. And in particular, one such example is the local curve now in Calabi-Yau 5. Now in M theory, you really need Calabi-Yau 5, so that's really where the Calabi-Yau condition is. So a local curve in Calabi-Yau 5 is a curve with a rank 4 bundle over that, such that the total space is Calabi-Yau. And of course, its relation to enumerative problems in Grove-Witten theory, that again, a very old subject, goes back to early work. I mean, very old, not early, old classical work of Kummer and with Gapa Kummer. And then with Nikita, we've generalized it to a set of conjectures that really equate the K-theoretic Donaldson-Thomas invariance with some M-theoretic computation. So anyway, the target space description of a local curve in M theory, that is that in that general list of things that can be described with quantum groups like that. And we're near the end of the talk. I didn't know how much information I should have put. Maybe I should have put more information, but anyway, that's all. Maybe let's leave more time for questions. And so to finish with the New Yorker, so maybe I can put the New Yorker cover back on. So this is another New Yorker cover, a very famous one by Steinberg, and which I artistically slightly modified to include like a view of enumerative geometry from around where I am. And that's we took a tour that started with kind of classical problems in enumerative geometry, went by the KDV and the Tutoda, and crossed over the Donaldson-Thomas bridge, and by the Donaldson-Thomas Avenue came to the M-theory Avenue. And if you'd like to know more about elliptic stuff, then about the elliptic stuff I've been teaching in courses. It was called summer course, but now of course we're almost in December, but the course still continues. But you can, the old videos you can maybe watch, and that's. I thank you for your attention, and maybe that's where I would like to stop.
Thank you very much, Andrei, for a wonderful talk. There have been a number of questions in addition, so I will read them. Arnav Tripathi asks, is there an intuitive reason why the tau expression you wrote down should be thought of as a theta function or determinant of cosmology?
This is actually, this is Well, since it was just wrote down, I'm trying to locate when I was in the talk and at that moment in time. I can see the questions in Q&A. Does it relate to the Witten's conjecture, or did it relate to what? I think maybe instead of trying to understand the question, I'll try to give an answer more generally. So I think what one can do is one takes the target space description of Grom-Witten theory for P1, and that is really described in terms of fermionic Fock space. The matrix elements, in particular, the P1 partition function is just vacuum matrix element of in that Fock space. It means it's some determinants of some matrix. So a matrix element in fermionic Fock space it's the determinant, it's half infinite determinant. So that determinant that's a way to that's what people call the tau function. And if you think of this kind of modular one-dimensional shift being embedded into this some sort of Grassmannian biomap that I described, you'll see that since it's embedded by sections of some twist of your sheaf, that the determinant of cohomology there will be the determinant I'm discussing here. So that's maybe that.
Okay, so then the question by Pavel Safronov, who asks, do non-numerical invariants of P1, such as quantum cohomology, Fukaya category, also have an interpretation in terms of 2 Toda?
Quantum cohomology is numerical. It's so the structure constant of quantum cohomology that's really those are numbers. Those are described by equations like this. Now, if you talk about category, it's a very interesting question. There is a categorical. This is a very active area of research. There is a notion of categorical aromatics, categorical Young-Baxter, categorical action of quantum groups, and so on and so forth. There has been a few computations that really do suggest that this should be many things I discussed should categorify, but those are really hard computation, because generally speaking, this is if you actually want to compute something categorical stuff, that's usually very, very hard computation, and you can also do in very special cases. So I would imagine there is a categorification to all of this, but I don't think I can cite results.
Very good. There's a question by Vasily Manturov, who asked, we have Young-Baxter equation at least on book covers. Do we have semi-infinite braid groups representations or semi-infinite topological quantum field theory, invariance of knots or three manifolds, etc.? And which of the above?
That's absolutely. You should read. Is Mina scheduled to speak on the series? Mina wrote like a sequence of papers. So it's both about the categorification and the invariance of knots and three manifolds. So there's a classical story. Goes back to Witten again, and Rusty Haftarov and many other people. I apologize if I missed somebody. That says that the old quantum groups, the ordinary quantum groups, they're related to invariance of three manifolds and knots and so on and so forth. And that story had many ramifications, and in particular, I believe you just heard Witten himself just gave a talk in this series a couple of days ago, but more specifically to what we're discussing here, there has been a recent one by Mina. The work is maybe a couple of years old, but it became available relatively recently. It's a work by Mina Aganagic about using this sort of input for categorified not invariance three manifolds and so forth. So that's really a huge chunk of knowledge which I won't be able to summarize here, but it exists. It exists. It's very impressive, and I invite you all to learn it.
Also, which of the above, he asked, has tropical counterparts?
I don't know. Maybe I'm blanking on a good answer to that question, but maybe I'll answer some different question. So so a different question, which is about general kind of wall crossing, kind of piecewise linear, piecewise constant behavior in mathematical physics. And so tropical variety is like a variety which is piecewise, in some kind of essential piecewise linear variety, which is, and that's so maybe this belongs to this general category. And then so I think the thing I find really worth exploring is that if once you go to the elliptic world, then your piecewise linear, piecewise constant behavior becomes actual analytic behavior. That's the way to think about it, is that if I have like a degeneration of a Abelian variety, that the degeneration of a Abelian variety is some union of projective or toric varieties that is described by some kind of picture that could remind many people of toric geometry. And but if you actually work in the actual elliptic theory, then you are having, instead of having walls and chambers, you're having just one analytic behavior, which is I think super cool. I didn't have time to talk about this in the lecture, but I think it's something I find mesmerizing.
Very good. I believe that's the end of the questions, and let's thank Andrei for a beautiful talk. Thank you.
Yeah, thank you very much, Andrei. That's very nice.
Oh, my pleasure. Thank you so much.
Okay,
Thanks
thank you.
everybody for listening. I was really a pleasure and honor. Yeah, thanks.
Okay. Bye.
Bye-bye, everybody.
Bye-bye.